extremely sorry again about the delay. So what we're going to talk about today was what we left from last time. Um, and this is one of those topics which some of you in the audience are actually better suited to teach. But I'll try to do an attempt at it, trying to bring some insights from how I think about it. It's traditionally a machine learning topic, whatever that is. And however, I also feel that it's a extremely powerful and an extremely intuitive, but a weird algorithm which, when it works, but very hard to conceive if you think about it from first principles. We'll do that, but first thing that we have to finish off is what we discussed in the last class, which is we were discussing about what is multiple linear regression. The idea is simple. You have multiple covariates or predictors. You want to estimate the relationship between y and x, and in the 1D setting, you fit a line, and that tells you what is happening to y as a function of x. If you have multiple such x's, example in this case, then you're fitting not a line but a hyperplane, right? And in this case, it's a 2D hyperplane because these are 3 dimensions. I increase one more dimension and there's no way you can plot it. You'll not be able to visualize it. Overall, the goal is that you figure out that hyperplane, which again minimizes these residual differences that you have from the hyperplane, right? So those are perpendicular distances to the hyperplane that you are trying to minimize overall. Not perpendicular, these are distances just from the surface of the hyperplane, not perpendicular to it. This distance is, so if this is your this is your y, that is what you're trying to predict. So each y corresponds to having certain observations. So this is x1, x2, and then there will be corresponding y to this. Right? So trying to look for a hyperplane, and I got an 8 or a 7, I think, in my I got a 7 in my engineering drawing, so I will never be able to do justice to this. Actually, I got a 6, I think. I got a 6 in my engineering drawing, so I'll never be able to do justice to it. And I'll tell you the story of that, how that grading is done for engineering drawing. Anyone knows how the grading used to be done for engineering drawing? It was chill. So in my time, engineering drawing is a first year subject for, just for context. Sorry, I'll take a tangent. The hypothesis was they put your names on, they keep boxes of different lettered grades at the bottom. They take your names or roll numbers, they make chits out of it, they put it on the fan, and they switch on the fan, and whichever box the chit drops down to, that's your grade. So it's purely random as it can get. Anyway, that's a separate discussion. But here, what you're trying to measure essentially is from each of these variables, overall, what is the difference between what you predict, which is your y, from your predicted y hat. The distribution is the same. It's just that that distance is from that hyperplane. That hyperplane in this case is being determined by what is x1 and what is x2. Right? So for each x1 and x2, there is a lot of possibility of what y can be. Right? So think about it in 3 dimensions. Your x1 and x2 are your 2D plane. Your hyperplane can be like this, can be like this, or can be like this, can be like this. The distance of what is the value on that hyperplane is for a corresponding x1 and x2. You want to minimize the distance of the yi's correspondingly. Similar to what you were doing in linear regression, in simple linear regression, except that now you are in higher dimensions. Right? So this is your planar surface. You have x1 and x2 distributed. Right? So this is orthogonal. So they are independent. For each of this x1 and x2, you have an incline that is possible. And with that incline, what you're trying to measure is what is that best possible incline that will give me where the sum of these differences will be minimal, right? Very similar to this case. You just have to think about this in 2D, and your grades do not determine whether you can think that or not. Right? So I can think despite having not gotten a good grade. So this is what that residual is. Correct. Yeah, z-axis. In this case, this is y-axis, which is because that's the measurement, but that's z-axis. Yeah. Okay. Okay. Any other questions? Okay. So we did a very simple problem where we looked at that age is a. We wanted to understand whether how does the blood pressure change with a function of age, and what is also something that we need to adjust for is that the birth weight, right, whichever unit it is in, is also being measured. We want to adjust for that fact. And the way we can simply think about this problem very simply is you can regress out, you can run a linear regression where you just, in an ideal setting, if blood pressure only varied as a function of age, then you would just run this model. What this model does is it does not actually account for that even people with same age can have different weights, and those people who have different weights within the same age can have different blood pressure. So this simple model does not adjust for that particular fact. So you can make this also, you can also compare this against the estimates that you're getting from what happens if you regress out birth weight simply. So the coefficient there is, in this case, is 0.15, and in this case is 6.15. One discussion we had last time was this is in the same scale that you originally got the data from. At this point, you cannot compare 6.15 and 0.15 because those are on different scales. The reason one of those numbers is higher will be clear from the actual scale of the data. Age is in terms of days, birth weight is in hundreds, and blood pressure is in hundreds. So if I have to go from here to here, my coefficient will be smaller if I keep the scale the same. And if I have to go from here to here, I have to multiply it by a larger factor. And that's essentially what you see here. In the case of age, you get 6. In the case of birth weight, you get 0.15, right? We ameliorated this problem by standardizing it. That's where we ended. You can standardize something by simply removing the effect of the scale. So you can bring them to the same scale. And the simplest way to do this is you just multiply this. You just subtract the mean and divide it by the standard deviation. Now everything is in the same scale, right? Varies around the mean, and all of them have similar variances. In this case, we haven't done that. This is fair to do because we're not going to make any conclusions about or the comparisons between the individual slopes at this point. What we are interested in is are these two models, are these two variables sufficient to explain the variability that we see in the data? So in the simple linear regression setting, we had seen that estimate is what is your mean estimate, which is your point estimate. Attached to it are 2 or 3 different quantities. One is your standard error, then are your t-values. So this is a t-test, and then is attached the significance to it. And what generally you're interested in is, do I need all of these? Do I need both the variables to capture? And a simplest way to think about whether you need all these variables or not is to look at these p-values, right? You could look at if a p-value is significant. That definition is something that you will already have defined, which is 0.05. Then below 0.05, if the p-value is greater than 0.05, you will fail to reject the null, and the null in this case is beta 1 is equal to beta 2 equal to 0, right? That is what the null hypothesis that you begin with. The test, however, that you're doing at each of these steps when you are calculating the t-value is an individual test. When you begin, your overall hypothesis is there is no effect of any of the covariates. When I calculate for birth weight, my null is this, and similarly for age, my null is this. The p-values that you're seeing is on each of these axes are testing for this, right? So at this point, if I had hundreds of such variables, right, I had two variables. In this case, both of them turned out to be significant. So I'm going to say that both of them are significant. I'm going to keep it. If you had 500 or 1000 of these variables, how would you come up with a very simple strategy to, what would be your strategy to figure out which variables to keep, given what I told you about how you would do it in the two case? If the p-value is significant, we keep it. If the p-value is not significant, we remove it, right? So these are some of the questions that you will ask if you're given a regression setting. We're coming on to what exactly problem we are going to focus on. So the first problem that you'll be asking is, are any of these predictors, is at least one of these predictors useful in predicting the response? The next question, which is this question, the next question will be, do you need all of them? Or that is the third question here. The second question is, how does it actually fit? How well does the model fit your data? So whatever model you have, is there a measure of the fit that you can give, how good that particular fit is? And finally, you can ask this question about, given a set of predictor values, what response value should we predict and how accurate is our prediction? And today we'll quickly focus on all four of them in a very, very surface level manner. The goal is to give you intuition about how to actually think about all of these four problems. So the first problem, does a relationship hold, right? That is a test for the simplest hypothesis which we had, which is beta 1 to beta p is equal to 0. That's what essentially you're going to say. That's your null hypothesis. The alternate hypothesis in this case is at least one beta p or beta j is non-zero, right? The question that we are asking is there at least one predictor variable that explains or that has linear relationship between that variable and the response, right? That's the first question that we are trying to answer. And this is the test of that hypothesis. If you focus on what test statistic do we need to test for such a hypothesis, it boils down to testing for variances. Our original question about regression, there is nothing special about regression. It's essentially a question about any model, if it is doing the right job, should help me explain the heterogeneity that I see in this data. So there is variation that I'm seeing in this data, and I want a model to be able to tell me that there is variation, because I want to use it in the future to predict what will happen. And this variation is in some sense actually information. So you want to capture it. You want to capture it to be able to explain what is going to happen in the future. And this essentially, when you're testing for this hypothesis that none of these variables are important, right? So none of these are actually going to inform what is your response. That is the simplest and the most dull model that you have, right? Which is, in this case of simple linear regression, is this flat line where all of them, the slope is 0. When you consider multiple different predictor variables, it boils down to asking that, when you take all of these overall, whatever number of variable predictors do you have, once you fit them, how much variation now? So this was your H0 and this is your model. Among the variation that I saw previously, how much of it can my model now explain? And that becomes your model of, so this is your total sum of squares. When you fit a model, the model will start to fail and you will have residuals. In an ideal scenario, you will want your residual to go towards 0, so that the explained sum of squares, which is how much your model can explain it, tends towards TSS. So quick statistic, a very quick statistic that involves testing this, whether model is doing anything meaningful, is to test for whether the explained sum of squares is close enough to 1. Right? You want this ratio to be high, which is, or you want overall this version, sorry, this is not with respect to TSS, this is with respect to RSS. But the analogy is similar. You overall want that ratio to saturate. And one way that you're going to test this is it's a test of variance, where the first variance comes from your model, and the denominator or the which is what is not explained by the model, and which is explained by the model, and on the denominator you have the variation which is not captured by the model, right? This is residual, which means it's not being able to capture, and you want overall this ratio intuitively to be high. That also becomes your test statistic, right? This becomes your F statistic. Again, that F came from Fisher, and this distribution, the reason we choose this distribution is because we know certain good properties about this distribution. This is essentially a distribution of two different chi-squares with different degrees of freedom. The intuition here is, ideally, in an ideal case, you want this to go towards 0 and this to go towards TSS, right? This to go to, towards, sorry, this overall term will go towards TSS and this will go towards 0. So it has to be a high number overall. That is what your hope is. And what we know from certain properties, which we are not going to cover, is on an unexpected level, the bottom denominator is sigma square. And if your null hypothesis is true, the expected value of that ratio is actually sigma square. The numerator expected value, if the null is true, is sigma square. The denominator expected value, if the linear assumption holds, is also sigma square. So this distribution is expected to hover around 1. That's something that will happen if the null is true. If you want to project, or if you want to show that this model does not actually hold, which is, or this null does not hold, we are looking for evidence towards this ratio being very different from 1. Right? Is that idea clear? Okay. This ratio, because under the null, in the linear assumption case, this expected value of the denominator, which is a chi-square distribution, is expected to be sigma square, which is your overall variance observed in the data. Yeah, that derivation we are not going to do in this class because it's a bit involved for this version of the class, right? So that's the underlying null on which it believes, right? But one simple way to think about this is this is your residual, right? So if even if you take your linearity assumption, this distribution will follow is a summation of we know this is normally distributed. We know this distribution will follow a chi-square distribution, and we know the assumption that we had made is this is sigma square. And this assumption essentially just says that the expected value of summation of those residual square is just going to be your overall variance, right? So we'll not do the formal argument, but hopefully you can intuitively see why that should be close enough to sigma square, okay? Because the variation y itself follows sigma square variation overall. So it hovers around sigma square value, and if you go close enough to it, your expected distribution of how much your residuals are varying, given the linear assumption is true, will hover around sigma square, right? Intuitively. yi minus yi hat, that's correct. I wrote yi minus yi hat. I removed that thing, but yeah, sorry. Yeah, I rubbed it, but it didn't rub properly. It's yi minus yi hat. Okay. Okay. So this is the what the F distribution encaptures, and this again we had a good and interesting discussion and a lot of tangential discussion last class. Hopefully, you've seen the stories. I think I learned also a lot in the process. But this is one of those distribution which follows, which is skewed and is derived from a scientist name. like the Poisson distribution. Um, it's essentially a test of variances, two different variances which you cannot estimate. The ratio of them follows an F distribution, and what you're looking for in a test value in a P test in a T test is how much amount of information is captured in this tail. So whatever is your observed, you have a prior distribution that you know. What you're looking for towards the evidence is whether this value, whatever you're observing, once you fit your model, is that significant or not, right? And the entire premise on which why we are doing this is because we are trying to find evidence whether whatever linear model I have fit, is that something that I would get by chance, or is there at least one variable in there which helps me explain these observations that I'm doing. You have multiple different variables, right? In the case of single variable, this is very easy to visualize because it becomes a simple t-test, right? In this case, it becomes a simple t-test. However, if you had p such covariates, you will do, you're welcome to do individual tests, and your linear regression method will also do individual tests. But the F test will tell you, is there at least one variable there which is able to explain the observations in Y, or which is sufficient to explain some amount of variance that is coming from one of the predictors. Right? That's the overall interpretation of why we use F test. Yeah, so the F test statistic is it boils down to, we'll come to it in just a bit. Like this will hopefully clarify. So this becomes a test for what's broadly called the analysis of variance. Right? What is the analysis of variance? It's the analysis of variance that you're doing for your model. So if you consider your sum of squares that are coming from your regression to be A and the residual to be B, it has certain degrees of freedom, which is degrees of freedom is 1, and in this case this is residual. So again, we've seen this again and again. This is n minus 2 degrees of freedom. Your F statistic is a ratio of the sum of the squares which are coming from regression divided by the sum of the squares of the residual. So divided by the number of degrees of freedom. So this is what your F statistic becomes. The overall goal in this case is we are essentially trying to generalize this to multiple degrees, this is something which will hold in general. So the regression, there's a concept of mean square, which is what is here. So the mean square is nothing but when you take the sum of squares and divide it by the total degrees of freedom, that becomes your mean squared version, right? And in this case, this is for n equal to 1, so that's why you see 1 there. But it doesn't have to be. It can be any number of covariates that you have in your data. This is the ANOVA for simple linear regression. We'll come to your question in just a bit. Right? So the first question that you can ask, for example, is there a linear relationship between this estriol level and birth weight? We can ask a similar-ish question. This is estrogen-related hormone. We are essentially asking that the level of hormone that's there in the mother, does it determine the birth weight of the baby? And in this case, we have a simple linear regression, right? We did not actually drill down upon too much of this problem, and you see why we are taking this tangent. This linear regression is very simple. This is your Y, this is your X. You're trying to essentially estimate the relationship between birth weight and estriol. What I'm going to pick up this example for is to show what does the analysis of variance here look like, how to interpret all the numbers that you see in your fit table. So you can fit your birth weight as a function of estriol. This is a different example. We'll come back to the age example in just a bit. There are a few numbers that you see here, for example, right? So what you see here is estriol, which is the variable or predictor. Estimate is 0.6. Your t value is 4.413. The F statistic in this case is 17.16 with 29 degrees of freedom. That's based on the number of observations, 31 observations. So n minus 2 is 29. You can also take the model fit and just run ANOVA, right? When you run ANOVA for this kind of setting, what it is trying to do is going to go and recreate this table that we have, which is, it's going to recreate the degrees of freedom that you have coming from your predictors. Again, there's only one predictor, so that's residual. That's estriol, excuse me. It's calculating all these different quantities, sum of squares, mean of squares, and then finally it's giving you that F statistic, which is basically the same F statistic that comes out of your summary output, right? So while you can focus on individual of these p-values, the F statistic is going to, if it is not significant, it will tell you that there is not even one predictor in your variable, in your data, which can help you explain the observation y, which is different from what you would have got if this data was distributed randomly. So in other words, this is a measure of, is there even signal in my data to actually do linear regression? If that number is close to 1, you will stop your linear regression right there, and because it will tell you that there is nothing informative. It usually will not happen in real cases because, of course, there is some amount of variation that you can always explain, but that's the use of this number F statistic. The F statistic will not collapse to the T value, right? It's going to be, because the T value is a measure of the difference of the individual estimates and not of the sum of the squares, right? The T distribution is different from the F distribution. Also, yeah. Does that answer your question? Yeah. Well, in some ways it will, right? If it is extremely different, right? That means that you have captured, the higher that number is, the lower is your RSS and the higher is your TSS minus RSS, which is how higher is good, right? So can you use this to compare two different models? Is that the question that you're asking? Yeah, so in sense you cannot. The reason you cannot is there is a conflating factor of how many predictor variables that you use here, right? So that has some information that will bleed in. So this is not the metric that you use to compare two different models. We will talk about model selection, I think in the next lecture. We'll not talk about the model selection in this lecture, but we have seen this in the other class, which is there are explicit criteria called archaic information criteria or Bayesian information criteria which are used, right? The way to think about model, how good is a model fit is to think about that, well, model fit you can use this, but if you want to do model comparison, you want to compare all possibilities that can happen, and one way to capture whether this model is better than this model is to ask that when I take both of these models and I try to predict this data itself again, what is the likelihood of being able to see these same exact observations, right? So those criteria, AIC and BIC, use your log likelihood to capture, well, how much amount of information that you're doing. Now you'll see that if you increase the number of parameters here, this is going to have higher information, because of course if you take a lot of parameters, you can inflate your log likelihood. So there is a penalty for the number of parameters, right? So don't worry about it at this point. This is minus log likelihood plus log k. The lower that number is, the better it is, right? You want that number to be lower so that your model fit is good. But we'll talk about it in when we talk about GLMs. Any questions about this? Okay. I know. Yeah, it's very small, right? It's very because in most cases the kind of data that we'll be dealing with will have some. It's something that you can simulate, for example, right? Like you can take y, you can simulate that to be a random Gaussian noise, and then x to be totally different distribution, and then you will see maybe f statistic will have absolutely no correlation, but always you will have something. We can do it right now, actually. You want to do it? Let's do it. So I'll just use the same example, but I'm going to totally change these distributions. So this is okay. Here, let's say 2 plus Rx. Rate is 0.01. Okay. Okay, so it's very close to 1 in this case, right? So you can do plot x and y, x1. And you can also visually see that there's nothing much going on here, right? And that's why that F statistic came to be. What I did very simply is I simulated y to be a random normal and x to be a random exponential distribution, and I did a xy test, and of course there's no relationship. That's what you get, F statistic to be a non significant one, right? That's same thing that your fit. What is it called? Sorry. Model 1. Okay. That's what your ANOVA will also tell you, that there is nothing here that explains what is going on in the data. So the p-value is not significant at all. Okay. Okay. Right. So variable feature selection, right? So we're taking some jump here. In an ideal scenario, again, what you want is you want to be able to capture. I don't need all these variables, for example, right? Do I need, if I have a data set with hundreds of these different examples, and that's what we're going to focus on today, do I need a lot of these variables to explain my entire thing? If you have a data set where you measured like 50 different variables, does not mean those 50 variables are actually equally important to explain what is going to happen in your data. And the variable selection, feature selection methods are something which will help you decide which variables to keep and which variables to not to keep. There is a whole science behind it, and there's a lot of stuff that goes on. I will talk about this very briefly, but we'll not do examples because I'm not a huge fan of either of these methods or the mix of these methods as well, because they're very abstract in some sense, right? They're very recipe based. We will talk about one methodology which helps you do this slightly more what's called mechanistically, so it gives you the interpretation of what is really happening. So let me just quickly introduce what it is. There are two ways to think about feature selection, right? So you have a predictor, you have multiple predictors. So let's say you have a predictor 1, predictor 2, predictor 3, predictor 4, and so on. And at each point, you will get, of course, you'll get p-value, right? So this is star, this is star, 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 null, maybe star, star. So from a very brief point of, I have, let's say, 5 different variables. I want to select the top 2 that I should take. How would you go about it? Right, this is the p-value. This is p1. P1 is the predictor. This is star. This is star. Assume that is a star. And you have beta p2 and p3. Both of these are 1 star each. This is 2 star, and p4 is nothing, and p5 is 2 stars. Or let me make it 3 star. Yeah. How do you go about? If I told you give me the top 2 features, I don't want to retain all 5 of them. Why? You'll see in just a bit, but intuitively more features are often bad because it's very hard to explain the model. So if I said, for example, the health status of a country is a function of its GDP, that's a nice model. Just one variable predicts everything. Whereas if I said the health status of a country is a function of GDP, the number of migrants that it has, the amount of funding that it gets from private sources, the amount of funding that it gets from public sources, it becomes complicated, right? In an ideal scenario, lesser variables to explain a particular observation is good, right? So how would you go about doing feature selection here? which features should you keep? We'll keep one. Which one? Which two will you keep? You'll keep this one. Star is the, yeah, you should know what is star. Star is here. This is star. So just to keep it consistent with that, I will just make it a dot. Right? So that's what I mean by star. It's the test of your significance. So star 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 means the p-value is close to 0. Double star means it's 0.001. 0.01 means star. 0.05 means dot, and everything else is empty. P2, P5, P1, P3. Yeah. So among the different people present here, I know a lot of you can teach this better than me, but that's a good idea. Yes. Okay. So you'll be able to do this. Yes. Correct. Why not just choose P2, P5 though? No, it's not lengthy. Okay. It's not going to be lengthy. Just first clarify that why it's not lengthy, because it requires only one sort operation. That's very quick actually. You sort by the p-value, you choose the ones which are the smallest, right? I could do that. But okay, now, yeah. Yeah. Why? Hmm. Good. Right. So, yeah, right. Correct. Yeah, fair enough. That's correct. So when we started the simple multiple linear regression setting, right, we did not make any explicit assumption about x1 and x2 and the different variables. If they're independent, that's great. That's wonderful, right? But usually it would not happen. You will have x1 informing, maybe this is correlated to x2, maybe x3 is correlated to, or x3 is correlated to x4. In an ideal scenario, all of them should be perpendicular, which means that all of them should be independent. So this should not inform what is happening here, but it can still inform. All of them should inform what is y. So let me draw it in a graphical fashion, right? So in an ideal world, you will want this to happen. Okay. Effect sizes. How will that effect sizes matter? Oh, I see. Okay, good point. So Aishwarya's point is that this coefficient might be significant, but if you look at it, its effect, assuming these are standardized, that's what you mean, right? They're all standardized. Assuming all the coefficients are standardized, so let's say this is 0.01 and this is maybe 1.1, right? So the change because of P4 to the y variable has a slope of 1.1, while this one is 0.01. This is significant, but this is not, right? So we'll answer that question in just a bit. But in an ideal scenario, if you had this stuff, if you start your multiple linear regression problem with this, right? It's a very simple problem, because at this point, if all of them are behaving independently, then it's possible that I will just pick up one of them and I will be done with it, right? So I'll run, if this is all independent, then I'll run regression. I'll get coefficients, individual coefficients. And since none of them are actually correlated at all, the estimate that I get this example is done actually in one of your vignettes, which I'm going to share. this estimate that you get, if all of them are independent, is going to be exactly the same as you would if you were to run each of these individual regressions separately, right? If none of them share any information, if none of them have any correlation, if I run my linear regression or multiple linear regression, then the coefficient estimates that I get from this will be exactly similar or very, very close to what you would get if I were to run these models separately, right? But in a real world scenario, of course, that's an extreme to happen, because everything else informs, the arrows indicate correlation, so everything else will inform everything else in some sense, right? And we want to essentially capture, if that relationship does hold, which 2 or 3 should I need, should I keep, so that I can inform my overall model to be the best model, right? Okay, we want to answer that question, that if significance is one thing, but if the slope is higher, which is the effects, which is usually, or in the statistical literature sometimes called the effect size, right? It's the effect size because this is the effect it is going to cause on your response variable. Then you can have a scenario where this is 1.1, this is not significant, but this is 0.01 but significant. Which one should I keep? Okay. You mean most of the independent, most of the variables have to be independent? Mm-hmm. Hmm. 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 Okay, so I'm not sure I fully understood the argument, but I partially understood it. I think let me reiterate, and hopefully it will make sense, right? So uh, we are in the statistical world, right? So in the statistical world, there is one metric that you choose, and that one metric happens to be p-value, right? So in this case, of course, you're right that you could, in principle, focus on what's called the effect size. That I focus on things which have a larger slope, but if that slope does not actually have much significance, then there is not there does not exist a statistical rationale to keep it, because what the model is trying to tell you is that even though that effect is large, it does include it, but it's likely something that you can see even if the model, even if you were to repeat this observation with a different set of model, because it will not reproduce, right? Like the statistical significance is not there, so this effect size will not reproduce. You're seeing it just because of chance in some sense. Oh, that's a good question. Okay, so now the next question is that, okay, you have looked at the statistical significance, and let's say now I make it that, okay, these two are both, or let's say all three of them have high statistical significance. Then which one should I keep, right? So should I only can choose two. Let's say this is 1.2 and this is 0.55. Which one should I choose? Is that the question? I want sparse models. Sparse models are good. Less information is good in this case, right? Complexity, no complexity, no neural networks required. Like simple models. Sure. This is all standardized. This is all standardized. This is all standardized. Yeah, that's a good point, right? Something you should always remember, that the coefficient does not make much sense unless you have proven that they're all on the same scale, right? Otherwise, of course, what you're saying is totally true, right? So if I compare uh, income in thousands of rupees versus lakhs of rupees versus crores of rupees, that scale itself will make the coefficient go up and down a lot. So you should not compare. This is all with standardized version, of course. So what should we do? Right. So I want to move on. So for the sake of time, so I'm going to give you what is done. This is, of course, like a lot of other things, it's an active area of research. Variable feature selection in itself is a full-on course. There are different ways to capture it, but there are two broad categories of models initially that were developed, right? This is, I'm talking about 60s, 70s, and maybe around those times. The first model is called forward selection. The idea behind forward selection is you start with the simplest model, which is the null model. Nothing is there. And then they do these regressions step by step. So take your 5 regressions, run all of those 5 regressions, add one variable at a time that produces the lowest residual sum of squares, right? So here at each of these points, I'm running 5 regressions, and let's say this one produces the lowest RSS, right? I choose that, and now this is my base model. I will now repeat the same exercise, including this as a fixed term, and figuring out among the remaining ones, P1, P2, P3, and P5, which one next produces, if I include it along with P4, which produces a lowest RSS, and so on. And that way, you know, if it is beta 3 and beta 4, then those are the two variables that overall help you explain the maximum amount of variance or minimum residual sum of squares. There is a stopping criteria. That stopping criteria could be that beyond a certain point, either I need a certain number of variables and I stop, or the residual sum of squares after including it, right, is similar to what you got previously, which means that at that point you don't need to include this because the residuals are not going any further down, right? So that's a criteria which is broadly used.